understand in better way. Let us assume that you have three keys, 10, 20, 30 or three keys. For same set of keys, there can be many possible binary trees. And we'll see few among it. Now 30, 20, 10. This is one binary tree. The other one 30, 10, 20. This is one more binary tree. 20, 10, 30. This is the other one. 10, 30, 20. And this is the one more. 10, 20, 30. Right. So how many trees we do have? 5 trees. How to calculate the possible binary trees from the given keys? The formula is T of n is equal to 2NCN by n plus 1. Now T of n is equal to 2 into n value is 3. 3C3 by 3 plus 1. 2 into 3 is 6C3 by 4. Now 6 into 5 into 4 by the formula I am writing, NCR formula I am writing. Six into 5 into 4 by 3 factorial. 1 by 4. This 4 I am writing. Now 4, 3 factorial is 3 into 2 into 1. 3 into 2 is 6. 6 will get cancelled and total is 5. This 5 is what? Maximum number of comparisons. So for the moment when you considered some elements or keys to construct possible number of binary trees, you can simply apply this formula. Then you will be coming to know how many possible binary trees will come from the given keys. So as far as this example is considered, possible binary trees are what? 5. So now I am considering the 5 to move. Now what you have to calculate? The maximum number of comparisons. Now we considered a binary search tree which gives a less number of comparisons. Now, so once check the maximum number of comparisons to search any of the element. So to search this 30, it is 1. To search this 20, it is 2 comparisons. To search this 10, we need 3 comparisons. In the before slides only, we were come to know that one relation, the maximum number of comparisons always will be equals to level of that tree. Now level of the tree is what? 1, 2, 3. So it is also required 3 comparisons, maximum comparisons. Now the level of this tree is what? 1, 2. So we need only 2 maximum comparisons. And 10, 30, 20. It is also 3 maximum. It is also 3 comparisons. Now, so we were drawn some binary trees and we got all 3 maximum comparisons except of this tree. So it is complete binary tree, right? For complete balanced binary tree, you got maximum number of comparisons or 2. So as of binary search trees belongs to a minimization problem, we'll take the less number of comparisons to solve the problem. We'll take only this tree. We'll not take all the trees because it is an optimization problem. We'll take whichever tree will gives you the low number of maximum comparisons, the tree. Then that tree will be going to considered in order to calculate the weight of the tree, the cost of the tree and this. So we'll take the other example to see. So now this time I am taking the example with the 4 keys. 10, 20, 30, 40. These are what? 4 keys. Now, what are the maximum number of possible binary trees? Just now I told you the formula, right? 2NCN by n plus 1. That is n is equal to be given with 4 keys. So now the possible number of binary trees are is equal to 8C4, right? 4 plus 1 is 5. I am just writing this formula. 8 into 7 into 6 into 5. And 4 factorial. I am just writing 4, 3, 2, 1. So this formula you already know from the mathematics, right? This NCR is equal to NC n minus 1. N minus R. That means NCR is equal to n factorial by R factorial into n minus R factorial. I'm just applying this formula, that's it. Right, now 5, 5 and 3 to 6, 6 and 4, 2 is 8. Totally 2 into 7, which is 14. That means 14 binary trees are going to considered for this problem. Now my question is, as the way you are increasing the number of keys, it is also quite natural, quite true that you will get more number of binary trees, and we cannot calculate all the trees and the cost of it, maximum number of comparisons. In the previous example and this example, previous example we have only 3 keys, but we got 5 binary trees. So drawing 5 binary trees, it's not a big task. But the moment when you are increasing the total number of keys, proportional to it, the number of possible binary trees also will get increased. Now here comes, we will take only few trees to calculate successful, unsuccessful. Once you know how to move forward, then you will be understanding which binary tree we can consider. So if I consider only one binary tree from this 14, maybe that 13 will have low cost, and that is the reason why we'll calculate cost of the binary tree, and we'll see that example how to we cannot take all 14, but we will take 14 binary trees in indirect way. We cannot draw it, will not draw also, will not take a big problem, will not take a big risk, but we'll be going to consider all this 14, because our aim is what? You have to reduce the cost of it. You have to consider the low cost which gives from binary tree. For that we'll take some formalized methodology, but as of now we'll work on this n equal to 4 to calculate successful and unsuccessful search, and what is the probability of successful search and the unsuccessful search, and we'll calculate even the cost of the tree. So it is, in the previous example we just calculated the number of comparisons and the level of the tree, but this example I want you to learn bit more, that is how to calculate cost of a binary search tree. So optimal is what? Now this time I am talking about optimal binary search tree. What do you mean by optimal binary search tree? A problem of optimal binary search tree is that if the key is given and probability is given, we have to generate a binary search tree such that the cost is minimum. So this is what optimal binary search tree. So just optimal word will come before of binary search tree. Optimal means correct solution. That means we have a constraint that it should be a minimum. So cost should be minimum. Then the binary search tree is called as optimal binary search tree. Now we'll proceed with this example. We'll take this example. Now my example 2. Now you given with some 4 keys. Now you asked to compute the cost of the tree. Okay. Now we'll proceed with the solution. How to calculate that, the same. So in the previous slide, we come to know possible binary trees for this example is 14. Okay. Now if there are n nodes, there will be n plus 1 square nodes. That also we were discussed, right? N nodes, then n plus 1 square nodes. What is your n value? 4. So that means you will be having only 4 nodes. So what is n plus 1 square nodes? That unsuccessful nodes will be 5. Now let's draw it. Now I'm just drawing here 20, 10, 30 and 40. So I'm not going to take 14, but I'll take few of it. 30, 20, 40, 10 and 40, 20, 10 and 30. Now you just draw the unsuccessful nodes, that means square nodes. So square nodes should be 5 according to the formula. Now make sure that you got 5 or not. You also draw with me so that in examination you feel more comfortable to proceed with the solution. So what these square nodes are called as, these are dummy nodes, because searching the unsuccessful key element is maybe possible, right? We will be asking the programmer to search the element which is not in the list. So once you done all the searching operation, then only you can conclude that search is failed or it is an unsuccessful search. So there are chances of having a successful search and unsuccessful search too. So now we'll take some probabilities of the same. So Pi is the successful probability, Qi is unsuccessful probability. I'm just writing some probabilities, 0.1, 0.2 and 0.1, 0.2. So when you add all this, it should give the one answer. So I'm taking in that way 0.15 and 0.5, 0.5. Now you may ask a question that why the reason you have taken P successful probability is 4 and unsuccessful probability is 5. So it is respective to the nodes. My probability Pi indicates probability for successful nodes. How many successful nodes you have? 4. Q represents that unsuccessful probability. How many nodes you have? 5. So it is respective to the number of nodes what are available. Now, so here what the thing will be going to do next is, we'll be going to calculate the cost of searching. Cost of searching a element from this tree, that I'm going to calculate. So now how can I calculate? There is a formula to calculate the same. Now let's take this tree and we'll calculate. The first tree I'm considering 30 and it is dummy nodes I'm taking 40. Now indicate the probabilities also. In the previous slide I mentioned the probabilities 0.1 and dummy node also having the probability. Now so this is what we are going to calculate the probability, the cost of this total tree. So tree consists of nodes, tree consists of square nodes, tree consists of circle nodes, tree consists of square nodes. So put together you'll get the cost of the tree. So the cost of searching 20 is what? It is in level 1. Cost of searching 20 is what? So 1 into what this 1 in, I'll write here 1 into what this 1 indicates, level. 20 is at level 1, 10 is at level 2. Now come to this one, very important, come to this dummy node. This dummy node is at which level? It is at third level, but I'm not coming to third level as element is not there. I'm at second level itself. But for appearance, you can find it is in third level. As you don't have any element, we'll not come to this, but our expectation is what element can be here. So we will take, if you consider it is 3, then we will take it is level -1. Did you understand? Now the same. Now I am just moving to calculate the cost of the entire tree. 1 into 1 indicates level and 0.2. 0.2 indicates probability of that node to search. It is it is 20 element cost. Now the next is what? 2. Level 2 is what? 10 element. Now I am writing that element. 2 into what is 2 indicates? Level. into 0.1. 0.1 indicates probability of this searching the 10 element. It is for 10 element, and for 30 take. 30 level is what? 2. And probability is 0.1. And plus 40 is what? 3. 40 is 3. Level is 3. And probability is 0.2. Plus. Now these are what? Successful search. I told you cost of the tree always is what? Collection or the sum of successful search and unsuccessful search. Even you have to calculate unsuccessful search. So in unsuccessful search, the first is what? It is 0.1. So you have to even write the level as you wrote for the other nodes. You have to write for square nodes. Square nodes first element is this, and the level you can find it is in 3, but actually it is in 2, because as element is not there, you cannot come to down, right? So you will take again 2. 2 into 0.1 plus 2 into 0.5 plus unsuccessful 2 into 0.1 plus 2 into 0.5 plus 2 into 0.15 plus 3 into 0.5 plus 3 into 0.5. Right? Now, so here I wrote here 3. 3 is what? Level minus 1. It seems to be level 4. That's what we were taken, level minus 1, which is 3. So finally, if you calculate, you will get 2.1. Successful nodes, that is started with 1 into 0.2 plus 2 into 0.1 plus 2 into 0.1 plus 3 into 0.2 plus unsuccessful node. So finally it is what? Cost of a binary search tree considering successful search and unsuccessful search. The formula is what? How the way I have calculated? Cost 0 comma 4, that means 0 comma n, is equal to probability, that is pi into, it is pi into level of ai, the nodes level. So it is not for single element. I wrote here I. So I value lies from 1 to n plus. How I calculated this cost? Probability of this plus qi into level ei minus 1. Right? Now, for it, I represented it is I. I starts from where? 0 less than I less than or equal to n. So this is what? Cost of this tree. To calculate cost of a tree. That means cost of a node is calculated with the probability and level. Cost of a tree is calculated with the probability into level plus it is what? Successful and it is what? Unsuccessful. Put together, you will get the cost of the particular binary search tree. Now, what is optimal binary search tree? Optimal binary search tree is, it is a problem to be solved, and the problem is what? That if the key is given and the probabilities pi, qi is given, we have to generate a binary search tree such that the cost is minimum. This is what optimal binary search tree. Now, so how I can apply dynamic programming on this optimal binary search tree, and what is the procedure to approach dynamic programming? We'll take an example in the next video and we'll be going to find the solution by applying dynamic programming. Thank you all.